this is my submission for chapter 30th exam. Part A states a long solenoid is surrounded at its center by a shorter coil, as in figure 1. At an instant when the current in coil 1 is 44 amperes and increasing at a rate of 2.5 amperes over seconds, the induced EMF in coil 2 is 1.30 times 10 to the negative 4 V. What is the mutual inductance of the two coils? So for this, we're going to use the formula. Well, actually, we're just going to divide our EMF times 10. And we're going to divide our rate. So our EMF divided by our rate. And this is equal to 5.2 times 10 to the negative 5th power H. Part B states, at this instant, what is the total magnetic flux through all the turns of coil 2 due to the current in coil 1? So for this, we're going to use the formula M times I, basically. So I1 in this case. So our M is what we got on part A, 5.2 times 10 to the negative 5th power, times our I that was given at the beginning of the problem, which was 44. And this equals to 2.29 times 10 to the negative 3 Webers. Webers. Part C states, the mutual inductance of two coils is 60. Find the magnitude of the EMF induced in coil 2 if the current in coil 1 is 35 amperes and increasing at 7 amperes over seconds. So for this, we're going to use the formula E is equal to negative M times the derivative of I di dt, or just times di dt. And this is equal to negative 60 times 10 to the negative 6, which we were given here, but we're just going to put it in scientific notation, times our rate, which is 7. And this is equal to negative 4.2 times 10 to the negative 4th power V. But our answer, we're going to write it without the negative sign. Part D is asking us to find the magnitude of the EMF induced in coil 2 if the current in coil 1 is 28 amperes and constant. So for this, we're going to use E is equal to di divided by dt. Well, this is equal to 0. And we're just going to set this to 0, I guess. Well, actually, what am I doing? I'm sorry. E is equal to di divided by dt. And di divided by dt is 0. So that is our answer for part D. For part E, I'm very tired. I'm sorry, I haven't had any sleep. Part E is asking us to find the magnitude of the EMF induced in coil 2 if the current in coil 1 is 26 amperes and decreasing at a rate of 5 amperes over seconds. So for this, we're going to use the formula E is equal to negative M di over dt, same thing that we used for part C. And then this is equal to negative 60 times 10 to the negative 6 power times negative 5. And then we get 3 times 10 to the negative 4th power V. All right. For part F, For part F, we are asked a toroidal solenoid with self-inductance of 76 has 465 turns of wire. Find the magnetic flux through each turn when the current in the solenoid is 12 amperes. So for this, we're going to use the formula L is equal to N B divided by I. And then we're going to solve for this right here. So this would be equal to Li divided by N. And then we're just going to plug our values in. So this would be 76 times 10 to the negative 6 power times 12 divided by 465, which is our turns. And this is equal to 1.96 times 10 to the negative 6 Webers. Part G is asking us to find the magnitude of the induced EMF in the solenoid when the current is 12 amperes and decreasing at 55 amperes per second. So our di over dt is equal to the 55 amperes over seconds. And we're going to use the formula E is equal to L d over dt, and this is equal to 76 times 10 to the negative 6 power multiplied by 55, and this is equal to 4.18 times 10 to the negative 3rd power V. Part H is asking us when a coil is carrying a current of 25 amperes that is increasing at 145 amperes per second, the induced EMF in the coil has a magnitude 3.7 MV. Find the self-inductance of the coil. So for this, we're going to use the formula L is equal to E divided by di over dt, and this is equal to 3.7 times 10 to the negative 3rd power divided by 145, and this is equal to 2.55 times 10 to the negative 5th power H. For part I, we are asked find the magnitude of the induced EMF at t is equal to 2 seconds if the current is I of t is equal to 225 amperes per second squared, t squared. So for this, we're going to use the formula E is equal to negative L multiplied by di over dt. di over dt is equal to, and we're going to solve, we need to find the di over dt. So moving things around gives us equal to 225 amperes per second squared t squared. And then our t squared is our time, which is 2 seconds. So this would be equal to 225 amperes over second squared multiplied by 2 squared. And this is equal to 9 amperes per second squared. So then we're going to use, again, our formula of E and plug this value in. So it would be equal to negative 2.55 times 10 to the negative 5th power times 9. And this gives us negative 0.02295 V. Or we're going to use the answer but without the negative sign. 0.02295 or 2.30 times 10 to the negative second power, as shown on the answer for from Mastering Physics. And last but not least, part J is asking, find the direction of the induced EMF at 2 seconds if the current is 225 amperes per second squared, t squared. So according to Lenz's law, the induced EMF should be directed opposite to the charge of the current. And because the current increases, this means that it will go opposite to the current. And this would be the answer for part I, opposite to the current. Thank you so much.